Hello guys, welcome back to the part 2 of the video on chemical equilibrium. So now let's discuss the salt of the third type, that is a weak acid and weak base. And taking an example, we have CH3CONH4, which is ammonium acetate, and this is formed by a weak acid and a weak base. And since both undergo hydrolysis, instead of writing separate equations for both, we can write both of them in the same equation. So we can write it as CH3CO minus plus NH4 plus H2O gives CH3COH plus NH4OH. This had initial concentration of C. This would also have initial concentration of C. And this is what is assumed in most of the books, because it's assumed that if CH3CO and H4 has a concentration C, then it undergoes complete dissociation even though it's not a strong electrolyte, but because it's a salt, it's assumed to ionize completely. So we assume that the concentrations of both are C, and this both would be 0, and finally it would be C into 1 minus H, C into 1 minus H, CH and CH. So for this equation, KH would be equal to CH3COH into NH4OH divided by H3CO minus into NH4 plus. So in this case, multiplying KH by Ka and Kb of CH3COH and H4OH, we get a very interesting result. That is KH into Ka into Kb is equal to Kw. And deriving this result is very easy just by multiplying the different terms. That CH3CO minus cancels with this, NH4 plus cancels with this, and whatever will be left will be just an H plus and an OH minus. So KH into Ka into Kb is Kw, and from this equation we can say that KH itself is equal to CH into CH by C into 1 minus H into C into 1 minus H. It turns out to be H square, assuming that H is much smaller than 1, so denominator is just C square, then numerator C square into H square. So we get H is equal to root of KH, which is equal to root of Kw by Ka into Kb, as we get from this equation. So next we have to find pH. So to find pH we need to have H plus concentration, and the easiest way to get H plus concentration would be from CH3COH. So writing the Ka of CH3COH, we get Ka is equal to CH3CO minus into H plus by CH3COH. So H plus concentration from this turns out to be Ka into CH3COH divided by CH3CO minus. Now CH3COH concentration equilibrium is CH, and CH3CO minus concentration equilibrium is C into 1 minus H. So C and C cancel, so you get Ka into H, and since H is equal to root of Kw by Ka into Kb, we can write it over here as root of Kw by Ka into Kb. So H plus concentration turns out to be root of Kw Ka by Kb. So finding pH from this, we get pH is negative logarithm of this. So taking the power half outside, we get it as minus half of log of Kw plus log of Ka minus log of Kb. So this becomes equal to, taking negative inside, we get negative log of Kw, which is pKw, negative log of Ka, which is pKa, and negative of negative log of Kb, that is minus pKb. So in this case, pH is equal to half into pKw plus pKa minus pKb. So this is one equation that's required, this is another, and this is another. We can write this in terms of KH as KH is equal to Kw by Ka into Kb. So this was all about salt hydrolysis. Next, let's move to the mechanism of buffer action, as to how a buffer remains at the same pH even though we add a little amount of acid or base. So now let's discuss the concept of buffer. So as mentioned in NCERT, a buffer is a solution that resists the change in pH even when acid or base is added. But in NCERT and even in many books, the reason as to why the pH remains constant is not mentioned. So I'm going to be explaining why the pH remains constant. So before that, we need to understand what's an acidic and basic buffer. So if you go through the book, it's enough, but there's a common confusion as to which is acidic buffer and which is a basic buffer. So acidic buffer is one in which there's a weak acid and a salt of it with a strong base. Even though the overall solution would have an alkaline pH, it is still considered an acidic buffer because it has an acid and a salt in it. Whereas a basic buffer is one in which there is a weak base and salt of it with strong acid. So even though the pH is below 7, that is the solution is slightly acidic, it's still called a basic buffer because there is a base and a salt in it. So let's consider the simple case of an acidic buffer, that is CH3COH and its salt with strong base, that is NaOH, that is CH3CON. So what happens when acid is added to this? When acid is added to this, the CH3CO minus ions that are present in solution due to weak ionization of this and this also combine with H plus to give CH3COH. And since this is a weak acid, it undergoes ionization to a very less extent to give H plus ion, so we can consider the pH almost remains the same. So when an acid is added, the CH3CO minus ions consume the H plus and form a very weak acid which doesn't contribute to change in pH. And when a base is added, the CH3COH, that's the acid itself which is present in solution, combines with OH minus to give CH3CO minus and H2. So this also does not affect the pH, so the pH remains constant even when base is added. Now coming to a basic buffer, we'll take the example of NH4OH, that's a weak base, and salt of it with strong acid, that is NH4Cl. So what happens when an acid is added to this, that is H plus ions? NH4OH plus H plus gives NH4 plus H2O. So this has no effect on pH. And next, when a base is added, the NH4 plus ion combines with OH minus ion to give NH4OH, and since this is a very weak electrolyte, it weakly ionizes to give OH minus ions which have a very small concentration, so it does not affect the pH much. So this was all about the video on the chapter equilibrium. Hope you understood these three concepts well, and if there are some other concepts that you find tricky in this chapter, you can always put in the comment section and we'll make sure that we make a video on it. Thank you so much.
Please do like and share the video and subscribe to our channel.